Hello, this is the second part on endocrinology. Today we're going to talk about homeostasis and about positive and negative feedback loops. You have heard of the term homeostasis probably many times before, including in the previous semester. I'm going to expand on that a little bit today because hormones are an uh, important mechanism by which homeostasis is achieved. A lot of hormones, what they do is uh, bring various parameters in the body back to their set points. So, what is homeostasis? It's the entirety of physiological mechanisms that make sure that the internal environment of the body is at its optimal state. What does that mean? That means that all the parameters that we can measure are at their most optimal level. So the temperature is just right, pH is just right, the levels of calcium in the blood are just right, the levels of glucose in blood are just right. So homeostatic mechanisms are all the mechanisms that ensure that those all those parameters are at the correct level. That correct level is called a set point. So there are all sorts of things that can move a parameter away from its set point. That you eat a bunch of stuff, there's going to be a lot of glucose in your bloodstream. There are going to be homeostatic mechanisms that are going to remove it from the blood and place it into the cells. For instance, insulin, a hormone, is going to do that. So homeostasis is a process, is a set of processes, or all the processes in the body that ensure that every parameter in the body is just at the right level. The problem with the word homeostasis is really the problem with the word. It's a linguistic problem because when you look at it, homeo and stasis, that means same or similar, and stasis means something static, unmovable. So if I asked you to quickly draw homeostasis on a coordinated system, with x and y axes, and x being time, and y is some kind of a level of some kind of a parameter, you draw a straight line at the set point, and if there's a disturbance that gets away from that line, you would have some kind of a mechanism that brings you back to that line. That line is absolutely horizontal. Unfortunately, it doesn't work all the time. Actually, it doesn't work at all, except with some very small exceptions. And it only works if that x-axis that you have is a very brief period of time, maybe minutes. Uh, at longer periods of time, it's not going to work that way. There are a couple of ways that uh, set point uh, changes, and it's normal. The set point is not always at the same level throughout life. Uh, there are a couple of different ways that it can change. The set point change is controlled. It's not going out of whack. It's not because you suddenly got overheated or something like that. It is controlled. It's the body's systems making sure that that set point changes. Um, One of those ways that the process can be ongoing is a developmental or ontogenetic change in set point. It starts with fertilization of the egg and ends up with death. That's a long period of time for a human who might live, 80, 90, 100 years plus those 9 months in utero. So the set point of something might change during life. The example that I like to give, and which is the one I gave in your handout, is the level of testosterone. As the early embryo starts developing, there's no testosterone in there, but relatively early in the embryonic development, the gonads develop. And the default is the female, but if there's a Y chromosome, there's an SRY gene, on the Y chromosome that starts a cascade of gene expressions that are going to result in molecules that are going to switch the developmental switch from female to male, and all sorts of things are going to change. And that ovary that just begun to develop is going to instead develop into a testes. That very early testes in a very early embryo is going to secrete testosterone. Testosterone is going to, in the early embryo, just diffuse. Remember, it's a steroid. It easily goes through the cell membranes because fat goes through fat. And is going to disperse through the entire embryo, all the cells that are still dividing and growing and stuff like that. And what testosterone is going to do is going to act as a steroid. It's going to go in there, find a nuclear receptor, and bind on to several different places in the genome, and turn on a whole bunch of genes. And those genes that are expressed in that moment are going to fundamentally change the properties of every cell in the embryo. We like to call that masculinization because it's testosterone, but it doesn't matter. What this process is an organizing effect of a hormone. It organizes the cells so they later can respond differently. One of the things that this is going to do is to make the expression of testosterone receptor permanent. Instead of being shut down and not responding anymore, every cell in the body will then have a receptor for testosterone active, being transcribed, translated. When it goes bad, broken down, the new one is made. What does that mean? That means that very soon, after a couple of days, the embryonic testes stops secreting testosterone. And again, if you measure testosterone in that early embryo, there's none. It's zero, and it's zero until it's born, and it's zero in a baby. It's zero in a toddler. It's zero in a preteen, and then teenage years come in, and puberty kicks in, and those testes now start secreting testosterone again and again and more and more and more. And the set point of testosterone gradually increases. So from zero, which is what all the homeostatic mechanisms would defend, if you inject testosterone, all the homeostatic mechanisms will go to destroy it and take it out of the body because it's supposed to be zero. But once you hit puberty, it's not zero anymore. And it gradually, over time, grows until it hits the adult set point, a very relatively high level of testosterone. But remember, all of the cells have been primed. All of the cells have testosterone receptor. They can respond to testosterone, which means that at this time, the secondary sexual characteristics are going to develop under the influence of that testosterone. You get an enlargement of the larynx, the Adam's apple, which deepens the voice. Uh, Different effect on the hair. For instance, I might get bald one day because of testosterone. Different distribution of fat, different distribution of muscle. It's a little bit easier for me to build up muscle than a woman. Uh, Development of male genitals, growth of those, growth of hair in various places, uh, behavioral effects. All sorts of things are going to happen because the cells in the embryo have been organized by that early burst of testosterone. And now they're responding to testosterone. Throughout that period, the set point has changed. So it started at zero, then it had a little bit higher. And if you did anything to that, put in more testosterone or testosterone blockers, the body would respond, defending that level of testosterone. Then goes back down to zero, and it's zero, 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 and then it hits puberty, and it goes a little higher. Now it's new the set point which the body is going to defend against, let's say, injections of testosterone or injection of testosterone blockers. Another year, another year, another year, another year. Now you're in your 20s, you're an adult, and it's this set point. And that set point is going to be defended by various mechanisms that keep it there. That doesn't mean that testosterone never changes during life. There are all sorts of effects that are going to change it. And there are effects that are going to temporarily change the set point that's defended. For instance, fatherhood tends to slightly lower the levels of testosterone. You're done fighting, right? You found a mate, you have babies. Now you don't have to be so aggressive anymore. Your testosterone can be a little lower. If your sports team loses or your presidential candidate loses, you are going to have a pretty long, maybe months, maybe even years, slightly lowered set point of testosterone. That doesn't mean just levels of testosterone, but set point that is defended by physiological mechanism. That's now the level of testosterone that physiological mechanisms are going to preserve. No higher, no lower. That's where you sit. And then gradually it can go back up, especially if your team wins again or your presidential candidate wins 4 years later, or stuff like that. If your country's bombed, testosterone is going to go down because you're defeated. So that's an ontogenetic or developmental change in set point. Much more common is the daily uh, change in set point. For instance, body temperature. Body temperature in the early morning, let's say 4 a.m., 5 a.m., so before you even woke up, is at its lowest of the day. The body temperature in the afternoon, about 4 or 5 p.m., is going to be highest of the day. This has nothing to do. Are you cold or hot? Are you going out in the heat? Are you going into the freezer? Are you exercising? Are you stressed? None of that. This is absolutely a physiological control of the set point. What controls it this way is the circadian clock in the suprachiasmatic nucleus of the brain. So circadian clock is going to make sure there's a daily cycle. There's always going to be a time when there's a minimum and time where there's a maximum. So each time of day is going to have a different set point, a slightly different set point. And that different set point is going to be defended. If your body temperature is let's say 36.3 Celsius at 4 a.m., that's the temperature that is going to be defended by, cooling you off or warming you up in case there is a disturbance. At 4 p.m., it might be 36.9. And at that point, 36.9 is what all your physiological mechanisms are going to try to revert to in case you exercise or get heated or get cooled or anything like that. And that happens every day of your life. Almost every parameter in your body, almost every set point in your body shows a daily rhythm that is driven by the circadian clock, which means there is a daily change in set point, usually a slight, and it's not a huge one, unless you are, let's say, a hibernating animal. Then it might be big between day and night or between summer and winter. But in humans, we are not very seasonal and we don't have these big ups and downs between day and night. So the set points are going to change relatively lightly. There are a couple of things that don't have any change in set point. One of those are levels of calcium, because precise level of calcium are essential for the proper functioning of nerve cells, muscle cells, and heart cells. So that is kept at a very, very tiny, narrow margins, and there's no daily rhythm of the set point. Another one is pH. You may remember that there are very, very narrow margins of correct pH in our body, 735 to 745. And so there's no daily rhythm and there's no ontogenetic change. It's always between 735 and 745. If your pH gets out of that range, you're probably in the hospital. The nurse is hitting the code button because all of your enzymes, all of those things are going to struggle to do anything because they're outside of their proper range, and there's going to be a lot of damage to all of your cells and all of your tissues. So the problem with homeostasis is linguistic, right? Homeostasis, it gives you a mental idea that it's all very stable, but it isn't. So back in the 1980s, culminating in a book in 1990, a Canadian biologist, Nicholas Mrozowski, argued that it should be changed, that the word should be changed into rheostasis, which means changing stability. A rheostat is what controls the temperature in your house. If it gets too cold, it turns on the heat. If it gets too hot, it turns on the air conditioner and always keeps it in various ways. But yet, if you measure the temperature in a home, it's going up, down, up, down, up, down over time. So there's a set point that you have set up on your rheostat. He wrote that book, Rheostasis, and actually there's a link to it. It's completely free now. It's 1990, where he gives a lot of examples of both developmental and circadian rheostasis, as well as seasonal rheostasis, mainly seasonal animals, and argues that we should use that word. Many physiologists have started using that word, not so much human physiologists, mostly animal physiologists, are starting to use it more and more. Nicholas Mrozowski, by the way, died a few years ago, but he was an absolutely stunning person. I had the privilege of meeting him a few times at scientific conferences. He was a very tall guy, kind of thin, with very gray eyes. He looks at you and you feel you're paralyzed or hypnotized. He was a scary guy. And he would go to poster session, scientific meetings. It's usually professors who give talks and graduate students who give posters. So it's all graduate students, and they're all scared. How are all these bigwigs in the field going to judge their work that they presented on their posters? And Nicholas Mrozowski would not look at 1,500 posters. He would pick two or three, and he would bring a chair. And usually, when somebody comes to a poster, you tell them what is on their work and answer their questions. Now he just waves you off, says don't talk. He sits down on his chair and reads your poster in detail, every graph, every word, everything. Then he gets up and either says this is crap, or he says this is great, and moves on. No more discussion. He goes to the next poster that he wants to see. So one day, I was one of those lucky or unlucky students that he brought the chair to. I had a poster and he sat down and I was sweating. I was so nervous. He sat there for, I don't know, 15, 20 minutes reading every detail of my poster. And then he got up, picked up his chair, said, it's great, and moved away. Oh my, that was the best moment of my life. So that's a little aside, a little anecdote, which I would normally tell in a lab when we are, chatting, but hey, why not? Okay, so far, everything that we talked about, homeostasis and even rheostasis, uh, had to do with negative feedback loops. Every mechanism that brings any kind of parameter from its wacky spot back to the set point is negative feedback loop. That's how you draw it, right? In a straight line or maybe a little wavy line, and something happens. Let's say your body temperature, you walk into a walk-in freezer and your body temperature starts dropping. Everything in your body that has anything to do with thermoregulation is going to kick in to bring your temperature back to the set point that is correct for that time of day. There are many, many, many well studied positive feedback loops. And in endocrinology, there are lots of them. Every time there's a need for the body to secrete a hormone for any kind of a function, the negative feedback loop immediately starts to shut it down. Let's say you start secreting thyroid hormone, right? The thyroid hormone is immediately going to feed back on the pituitary to suppress thyroid stimulating hormone, and to the hypothalamus to suppress the thyroid releasing factor. So there's always a negative feedback loop. Whatever goes, normally thyroid is zero, right? And when you need it, thyroid gets secreted, which means TRF has stimulated TSH, has stimulated thyroid, and immediately it becomes a negative feedback loop, stopping it, suppressing it, bringing the thyroid to zero. Every hormone has that kind of negative feedback loop. There are several bodily functions in which we don't have a negative feedback loop, but instead use a positive feedback loop. Positive feedback loop is not defending a set point. Positive feedback loop is intentionally taking a parameter away from its set point in order to uh, to reach a particular goal. This is not something that's happening all the time, daily. Da, da, da. It needs to probably takes a lot of energy. uh, it needs to be stimulated by something. It's not happening always, every day at the same time of day. This is something that happens in a specific time. There might be stimulus from the outside world or something like that, where that cell or tissue or organ needs to perform a major function that requires a lot of energy. And for that, it needs, let's say, whopping quantities of a couple of hormones or something else, which is very energetically expensive for the body, which is why the set point for those things are much lower. But the job needs to be done, and so we have a positive feedback loop in which instead of bringing stuff back to the set point, we have stuff bringing it away from the set point. So everything increases, and it's a feedback loop. In a negative feedback loop, you have, A stimulates B, B inhibits A, and everything goes back to normal. In a positive feedback loop, A stimulates B, which stimulates A to make more B. Both of them are stimulating C, which also stimulates A and B to make more C and more D, which is stimulating A, B, and C. Everything is stimulating everything else in order to make a really fast and big whopping effect in order to reach a particular goal. The moment that goal is reached, the whole thing stops. Why? It doesn't stop spontaneously. Well, those molecules are still stimulating each other. They naturally stimulate each other. What happens is when the goal is reached, one aspect of that cycle is going to be broken, which allows the negative feedback loops. They've been operating all along and trying, but they were too feeble to have any effect. Now they can. They can bring everything, A, B, C, and D, back to their normal levels. So, negative feedback loop is weak and trying to bring everything back to normal, but a positive feedback loop is increasingly adding a lot more energy and working really, really hard, and it's much more powerful than the negative. But once it gets broken because the goal has been reached, then the negative feedback loops have the capability of bringing everything back down. So your handout has several different examples. There's not many in the human body. Um, Probably the best known one and most studied one is childbirth. So, how does the childbirth start? Well, the baby decides the moment it starts. It's going to secrete some prostaglandins. Prostaglandins act in a paracrine manner. They act on the muscles of the uterus. The muscles of the uterus contract. You get a first contraction or two or three because the prostaglandins secreted by the baby are stimulating the uterus. What happens when the wall of the uterus contracts? It pushes the baby down towards the cervix. The head of the baby is going to press on the cervix. What does it mean? There are stretch receptors in the wall of the uterus, especially around the cervix. And when those stretch receptors are stretched, they're going to send a signal, a neural signal, to the brain. The brain is going to then stimulate the pituitary. This time it's going to be posterior pituitary to secrete the hormone oxytocin. Oxytocin goes into the bloodstream and goes all the way down to the uterus. And the reaction of the uterus, response of the uterus to oxytocin is to contract. So you don't need prostaglandins anymore because oxytocin is telling the uterus to contract. What does the contraction do? It stretches the stretch receptors in the wall. which sends more of the signal to the brain to send more oxytocin into the bloodstream. More oxytocin is going to trigger another and stronger and more frequent uh, contraction of the uterus, and baby starts going out and it's stretching that wall, and stretch receptors are stretched to the max and stimulating the brain to the max, and the brain is sending maximum stimulus to the posterior pituitary, which is just churning out all the oxytocin it has, and it's until the baby's born. The moment the baby is born, you have that break in the loop because nothing is stretching the wall of the uterus anymore. So the stretch receptors slowly go back and they're not sending the signal to the brain. The brain stops sending the signal to the pituitary. Pituitary doesn't send the oxytocin into the bloodstream anymore. And so the whole thing collapses because now the negative feedback loops, they were trying all along to put, oxytocin down. They couldn't. It was so much. Uh, they now can gradually bring oxytocin back to normal and the whole system back to normal. But it takes some time. It takes some time. So at the moment, immediately after birth, oxytocin levels in the bloodstream are still going to be very, very high. And the next thing is going to happen is you bring that, quickly washed and clean baby back to the mother to nurse. And nursing is another example of a positive feedback loop. So what happens is that the baby latches on to the nipple and, well, starts chewing, right? It's, milk, sweet, nice. What happens is that the nipple also has stretch receptors that are going to respond to being chewed on. And they're going to send a neural signal to the brain, which is going to send a signal to the posterior pituitary to actually secrete more oxytocin again. Oxytocin goes into the bloodstream and is going to reach the breast, where there's already a lot of milk stored, and it's going to let down that milk. That milk is now ejected out of the breast into the baby, and baby is going to say yum and is going to chomp some more, and more signal to the brain from the stretch receptors, more oxytocin in the bloodstream, more milk is coming out, and the baby's happily nursing. How does this stop? At some point, the baby is going to be satiated. It's going to say, I'm not hungry anymore, and it's going to unlatch. This is where it stops. So now the stretch receptors in the nipple are going to go back to their normal length. They're not stimulated anymore. So they're not sending the signal to the brain anymore. So the brain is not telling the posterior pituitary to secrete oxytocin anymore. And so there's no more oxytocin to tell the breast to release milk into the outside world. While all of this is happening, the mom's brain is full of oxytocin. Interestingly, the baby's brain also responds to this with the increase of oxytocin. One of the things that oxytocin does is it has some behavioral effects, and that is that rise of oxytocin is going to make you like the person next to you more. So media loves to talk about the love hormone. It's not love hormone because more you like that baby of yours, or oxytocin is released from hugging, from kissing, from copulation, all sorts of things. So you love that person or those people right around you more, but you like the other people less. So it's an in group, out group hormone rather than love hormone. More you love and want to protect people around you, more suspicious you are of people who are not part of your circle. So it's not a love hormone, it's an in group, out group hormone. Anyway, back to positive feedback loops. Another positive feedback loop happened 9 months before. Copulation is another positive feedback loop. Uh, Stimulation, you speed up until it's the end. You can read about them and figure out what hormones are used in both the male and the female during the copulatory positive feedback loop. Another positive feedback loop happens in the kind of same region of the body, and that is urination. We're going to go into more detail about that when we talk about the urinary bladder later in the semester, but it is a transitional epithelium, which, when the bladder is empty, is multiple layers of cells. As the urine slowly seeps from the kidneys through ureters into the urinary bladder, that liquid is going to gradually stretch the wall of the urinary bladder. As the wall is being stretched, all those layers of cells start moving next to each other and thin out. So instead of starting, well, let's say with 10 layers, and more there's liquid in the urinary bladders. This could be 9, 8, 7, 6, 5, 4, 3, 2 as they move around each other. And you want to burst if it's one layer, but it can potentially go to the one layer thickness. You're probably already urinating wherever you are at that point. And then as you start urinating, it starts emptying. Those cells start moving on top of each other again to rebuild those multiple layers. This is a positive feedback loop that cannot be stopped or reversed. And it's not going to stop until it's a multi-layer transitional epithelium again. You have already studied some positive feedback loops last semester. For instance, the action potential. The action potential in the nervous system, as well as the action potential in the heart, which we are going to soon get to, are positive feedback loops. Once you have the first sodium channel open at the axon hillock, it changes the membrane potential in such a way that the next sodium channel right there is going to open, and next one, next one, next one, next one, and you can't stop it until all sodium channels are open and all the sodium is surging through. And once it happens, then the cell membrane is at such a level that it starts opening potassium channels. And potassium channel, once one opens, it starts changing the membrane in the opposite direction, and that is going to open the next potassium channel, and another one, another one, another one, until all potassium channels at that spot are open and all the potassium is moving through it. So that's another example of a positive feedback loop. Another one, we are not going to go into great details about it, is blood clotting. There's a lot of blood clotting factors, like a dozen or so, and they each work in that way that the first stimulates the second stimulates the first. Both of them stimulate the third, and the third stimulates both first and third. And so there's a whole cascade of coagulation factors that are going to, they're all stimulating each other, and until there's a plug and it's all done, and then the whole system collapses. So positive feedback loops are rare, they're very energetically expensive, and they're used in situations when a big goal needs to be reached. So and it's usually at unexpected times. You never know when a neuron, that particular neuron, needs to be stimulated. You never know when you'll have the opportunity to copulate with somebody. You don't really know when your baby is going to start the birth process, or when the baby is going to be hungry and wants to latch on. So those are unpredictable in time, and they are energetically expensive, and they reach a goal, and once the goal is reached, it goes back to normal. So they're all going away from the set point, while homeostatic mechanisms, those are the negative feedback loop mechanisms, are bringing it back to the set point, to the normal situation, the normal levels for all of those factors in a normal situation, in a normal body. All right, I'll continue tomorrow. Thank you.